In this second part of the material on optimization, we are going to cover duality and optimality conditions for some of our continuous constrained optimization problems. So first, let's talk about duality. Taking the dual of a constrained problem is a process where a new problem is created. It transforms the problem, and in that new problem, the dual problem, the role of the variables and constraints is either partially or completely exchanged compared to the original problem. We say that the constraints in the original problem are dualized. For reasons that will become clearer, duality has a very close relationship with prices, market prices. So to get started, let's suppose we have an objective f that goes from Rn into R, equality constraints defined in terms of an equality constraint function g that goes from Rn into Rm, and inequality constraints defined in terms of an inequality constraint function h that goes from Rn into R to the R. And we'll consider the problem. We've seen this general type of problem earlier. The minimization over choices of x in Rn of f of x subject to g of x equal to 0 and hx less than or equal to 0. We define two functions associated with f and g. They're called the Lagrangian and the dual function. And after we've defined them, then we'll consider the relationship between those functions and minimizing f. So first, the Lagrangian. Lagrangian is going to be a function of three arguments, three vector arguments. The first is going to be x, my original decision vector, but my second two arguments, lambda and mu, are going to be vectors that have the same length as the number of equality constraints and inequality constraints respectively. So the Lagrangian is defined to be, Lagrangian of x, lambda, mu, is the objective f of x plus lambda transpose times g of x plus mu transpose times h of x. That function is called the Lagrangian. The variables lambda and mu are called the dual variables. And if we have a problem that doesn't have any equality constraints, we'll just omit the term involving those constraints. And similarly, if we don't have any inequality constraints, we'll omit the term involving those. Sometimes when we're defining a problem, we'll in fact introduce the symbol for the dual variables when the problem is defined by writing it in parentheses after the constraint. So, for example, you might see someone writing minimum x in Rn of fx such that gx is equal to 0 with then lambda in parentheses afterwards. So that's conveying that lambda is going to be the dual variable associated with those constraints. Associated with the Lagrangian, we're going to define another function. It's called the dual function, and the dual function has two arguments, lambda and mu, and it's defined to be the inf of the Lagrangian over choices of x. Function D is called the dual function. And again, if there are no equality constraints or no inequality constraints, the dual function is defined in terms of the corresponding slightly simplified Lagrangian. The dual function being defined as the inf, for a particular lambda and mu, it might take on value minus infinity. So most of the time it turns out we're going to be interested in the values of lambda and mu where the dual function doesn't take on the values minus infinity, doesn't take on the value minus infinity. So to make it convenient to refer to that region, we'll define the effective domain E of the dual function to be the set of lambdas and mu's such that the dual function is greater than minus infinity, not equal to minus infinity. So if I restrict D to E, in other words, think of it as a function not from Rm cross R into R union minus infinity, but rather think of it as a function from E, then it is a function onto the set of real numbers. Remember, we defined a convex function, and then I defined a concave function is minus a convex function, effectively. The usefulness of the dual function stems from its concavity. Let f, g, and h be functions. Let's consider the Lagrangian, the dual function, and the effective domain. It turns out the effective domain of the dual function is a convex set, and the dual function is a concave function on the effective domain. That particular property doesn't depend on any property of the objective nor of the constraint functions, and it'll be particularly useful as we develop duality. So One more definition. This section of the material is fairly definition laden, so if you're studying this, you might need to look over it several times and flip back and forth between some of the examples that are going to come and the definitions. Here's another result, this time a theorem. Let f, g, and h be functions. Let lambda be an element of r to the m, and mu an element of r plus to the r. In other words, the entries of mu are non-negative. Let's suppose x hat is a feasible point. In other words, x hat satisfies gx equal to 0 and satisfies h of x less than or equal to 0. So x hat is feasible. Then we have the following property. Then f of x hat is greater than or equal to the dual evaluated at any point, at that point lambda and mu. The d is the dual function. I haven't presented many theorems in this course, in part because we're mostly interested in the results and not so interested in the proofs. But this proof is so straightforward and I think gives some useful insights that I want to present it. Let's remember the definition of the dual function at a particular value lambda mu. It's the inf of the Lagrangian over choices of x. That's simply restating the definition. Restating the definition of the Lagrangian is the objective plus these additional terms, lambda transpose times g of x plus mu transpose times h of x, again by definition of L. Well, the inf over a set of points is less than or equal to the value of that function at any particular point. So let's plug in the point x hat. And what we obtain is that the inf over all x of fx plus lambda transpose g of x plus mu transpose h of x is less than or equal to f of x hat plus lambda transpose g x hat plus mu transpose h of x hat. That's just by definition of the inf. Remember, the inf is the greatest lower bound on the objective. And if we plug in the greatest lower bound on the minimization problem, on the problem, if we plug in any particular value, then the inf has to be no greater than that particular value. But g of x hat by assumption is equal to 0. So that first term is equal to that, second term there is equal to 0, and h of x hat is less than or equal to 0. So when I multiply it by a vector of non-negative numbers, the product is a number that's less than or equal to 0. So if I replace that by 0, I make the whole expression no smaller, perhaps greater. So that means that second last line is in turn less than or equal to f of x hat. So the dual function is less than or equal to f of x hat. That theorem and that result enables us to gauge whether we're close to a minimum of an optimization problem. In particular, for any value of lambda, for any mu that has non-negative entries, we know that the minimum of the problem is no smaller than the dual. So if we plug in a value of lambda and mu and evaluate the dual on the one hand and have a feasible point on the other hand, if the dual is not very far from the objective value at the feasible point, then we know we're pretty close to a minimum. By the way, we've taken the dual with respect to both the equality constraints and the inequality constraints, but we can also take the partial dual with respect to only some of the constraints. So from that basic theorem, we get a nice corollary. FGH are functions. The inf of my original problem is greater than or equal to the sup of the dual function over non-negative mu's. Sup over lambda and mu in the effective domain of the dual given non-negative mu's. Furthermore, if the problem on the left-hand side has a minimum, then the minimum of the original problem is greater than or equal to the sup. That result, that greater than or equal to result, is called weak duality. The right-hand side of 422, this problem on the right-hand side, the sup, is called the dual problem. And we say that the constraints in the original problem have been dualized. you'll notice in 422 that there are none of the original constraints. The original problem had constraints gx equal to 0, hx less than or equal to 0. They've been eliminated in the dual problem. We now have variables lambda and mu that correspond to the original equality and inequality constraints, and we've got new inequality constraints, in fact non-negativity constraints on mu. So that right-hand side is called the dual problem. The constraints in the original problem are said to have been dualized. And when we want to refer to both the original problem and the dual problem, we call the original problem the primal problem. Maximizing the dual problem is equivalent to maximizing a concave objective over a convex set, which is equivalent to minimizing a convex objective over a convex set. In other words, maximizing the dual problem is equivalent to minimizing a convex problem. So in principle, we could solve the dual problem using iterative improvement techniques. Unfortunately, if the inequality in either 421 or 422 is strict, that doesn't give us a complete insight into the solution of the original problem. When that inequality is strict, we say there's a duality gap. On the other hand, when the left and right hand sides are the same, we say there's no duality gap, or the duality gap is 0. And in that case, what we've done is we can evaluate the minimum of the original problem that had equality and inequality constraints by maximizing a concave objective over non-negativity constraints. In other words, solving a problem that's equivalent to a convex problem. In practice, though, evaluating the maximizer of the dual involves evaluating finding the inner problem, solving the inner problem, and indeed solving it in terms of lambda and mu, and then finding the supremum or the maximizer of that dual function over lambdas and mu. In some circumstances, the inequalities are equality, and the sup and inf can be replaced by max and min. So what happens is we have that the supremum problem becomes a maximization problem, and the inner inf problem becomes a min. So we've got an inner minimization problem embedded in an outer maximization problem. The requirements for these nice conditions to hold depend on convexity of the primal problem and other technical conditions, and we're going to develop some of those conditions. But in the next section, just to give a flavor of the usefulness of this result, we're going to consider an example where the conditions hold. We'll consider sufficient conditions later. In the dual problem, I'll emphasize again, the equality and inequality constraints have been transformed into terms in the Lagrangian, and the Lagrangian becomes the objective of the inner problem. So let's make this a little bit more concrete with an example. Let's consider the problem. I won't have any inequality constraints for now, just one equality constraint, where I want to minimize f of x subject to g of x equal to 0, where f is defined by f of x is equal to x squared, and g of x is defined to be 3 minus x. So this is a pretty boring problem, because if 3 minus x has to equal 0, then the only feasible point is x equals 3. So it's actually pretty easy to solve the problem. Nevertheless, we're going to take the dual with respect to the equality constraint and figure out how to solve the dual problem. Of course, if we could only solve trivial problems with our dual approach, it wouldn't be much use to us, but the attractiveness of duality is that even when the problem's not so trivial, we can take a similar approach to solving it. So we're going to start with a trivial primal problem, solve it using duality, and then later on we'll see that that general approach has some generalization. We can generalize it to more general problems that are not trivial to solve. So first thing we need to do is evaluate the dual, which involves evaluating the inf of the Lagrangian. Remember, we want to maximize the dual. Since there's no inequality constraints, we're just going to consider one vector argument of the dual, namely lambda. And for all lambda in R, there's just one equality constraint. So D is a function of lambda, which in general is a vector, but in this case is just an element of R. And it's by definition the inf over choices of x of the Lagrangian. The Lagrangian is equal to the objective, which is x squared, plus lambda transpose times the equality constraint function. Since we've only got one entry in the equality constraint function, we don't need to explicitly take the transpose. We've just got lambda times 3 minus x. So I want to take the inf of x squared plus lambda times 3 minus x. Let's make careful note of what is constant and what is a variable here. Although we're going to need to calculate this for each possible value of lambda, when we're evaluating the dual for a particular value of lambda, lambda is fixed. On the other hand, x is the decision variable, so to speak, in our inner infimum problem. We want to find the x that makes this as small as possible. Lambda is notionally fixed. Well, I'm sure you've solved using calculus how to minimize this problem, but that's in fact a special case of solving a general unconstrained problem. Since we haven't written down the optimality conditions, I'm going to solve this directly by completing the square. So I can take x squared plus lambda times 3 minus x and re-express it as x minus lambda on 2 all squared plus 3 lambda minus lambda squared on 4. You can check that this expression here is exactly the same as the expression in the previous line. Remember that lambda is constant. We're trying to, for a given value of lambda, we're holding it temporarily, we're holding lambda temporarily constant, and we want to minimize x, minimize over choices of x. So 3 lambda minus lambda squared on 4 is fixed for fixed lambda, but the term in the squared, of course, depends on x. How could we make it as small as possible? Well, it's the square of a real number, so it's no smaller than 0, and by making x minus lambda on 2 equal to 0, we make this squared term as small as possible. In particular, if I set x equal to lambda divided by 2, that will make the term in the squared 0, and that's as small as it could be. That will leave us with the term 3 lambda minus lambda squared on 4. So we get the result that the dual function for a particular lambda is equal to 3 lambda minus lambda squared on 4. But that derivation is true for any particular lambda. So what we've just shown is that for all lambda, the dual function is given by d of lambda is 3 lambda minus lambda squared on 4. Well, that is a real, for any given lambda, that results in a real number. So the effective domain of the dual function is the whole of the real numbers. Moreover, d is quadratic and strictly concave. So the dual problem has a maximum, and we can evaluate the maximum. Maximum over choices of lambda in R, which is the same as E of the dual, is the same as maximizing over lambda in R, 3 lambda minus lambda squared on 4. Again, completing the square, I can rewrite this as, this time, minus the square of lambda divided by 2 minus 3, all squared, plus 9. This time I'm trying to maximize the dual function, and I've got minus the square of a number. The largest that minus a square of a real number can be is 0, and so if I can set this equal to 0, the term inside the large parenthesis equal to 0, I will have found the maximum value that this term can take on. Well, indeed, if I set lambda divided by 2 equal to 3, or lambda star equal to 6, I will have made minus the square of lambda on 2 divided minus 3 as big as possible. Setting lambda star equal to 6, I get this expression as 0, and that leaves me with 9. So the maximizer of the dual is 9. The maximum of the dual, I should say, is 9. The maximizer is lambda star equals 6. For that particular value, lambda star, if I ask what's the minimizer of the Lagrangian, Well, from the previous page, we know that for a particular value of lambda, the corresponding minimizer of the Lagrangian is that lambda divided by 2. So the minimizer, the corresponding minimizer of the Lagrangian is x star is equal to lambda star on 2, 6 divided by 2, or 3, which, by the way, is the minimizer of our original equality constraint problem. So what we've just done is we've solved the original primal problem, which had equality constraints, actually just one equality constraint, by solving the dual problem. The dual problem did not have any equality constraints. It did have a variable lambda that corresponded to the original equality constraint, but it did not have any equality constraints. Since the minimum of the original problem is also 9, and the maximum of the dual is 9, there is no duality gap. The particular value lambda star, which maximized the dual, is called the Lagrange multiplier for this problem. And we'll carefully define and generalize that notion in section 441 and subsequently. The reason why duality is so important is because of its economic interpretation. So let me make such an interpretation. Let's say in an economic dispatch interpretation. Let's suppose F is the operating cost of a generator. Again, we'll mostly be concerned with the situation where we've got multiple generators, and this story generalizes to multiple generators. But for now, let's just pretend we have one generator. Let's suppose that the demand was 3. And so our supply-demand constraint was that 3 minus x is equal to 0. That is, the demand is 3, and we want to meet the demand with production or supply x. When we look at markets, we're going to need to define prices. And let me use the symbol pi for price. And I'm going to imagine that we have a generator, and somehow it's going to sell its production into a market, and the market price is going to be pi, and it will receive that price for all of the units of its production. So it produces x, the price is pi, and that means its revenue is pi times x. On the other hand, its production costs are f of x. Let's look at the decision-making process of the generator that is told that there is a price pi for its product. First of all, let me observe that the revenue minus the production costs is called the operating profit. Whatever's left over from the revenue after it pays for what it costs to make the energy, or in general its product, is called the operating profit. We're going to model the generator as an entity that wants to maximize its operating profit. In other words, the generator we're going to model as an operating profit maximizer. That is to say, it will seek to maximize the difference between its revenue minus its production costs. Since we've mostly discussed minimization problems, I'm going to think of an equivalent problem of minimizing minus that objective. In other words, minimizing production costs minus revenues. That may not be a perfect model of decision making, but it's a reasonable start at trying to model how market participants could be expected to behave. Let me emphasize that operating profit includes production costs, but doesn't include the fixed costs of equipment or any other costs that are not affected by operating decisions. So we're just considering the operating costs or production costs that are affected by operating decisions. Well, I'm going to observe that if the price is set equal to that Lagrange multiplier lambda star, then a generator trying to maximize its operating profit will be motivated to meet the demand. So again, the operating profit is revenue minus production cost. If we set the price pi equal to lambda star, then the revenue will be lambda star times x minus f of x, and it's going to try to maximize its operating profit. Let me observe that the Lagrangian, evaluated at x and lambda star, by definition that's f of x plus lambda star times 3 minus x. If you compare that to the operating profit, you will see that it's equal to minus the operating profit plus a term that is independent of x. In particular, Lagrangian is equal to minus the operating profit minus the operating profit plus lambda star times 3. Well, if we wanted to maximize the operating profit over values of x, we could have equivalently minimized the Lagrangian over values of x. But we already know that the minimizer of the Lagrangian, L of x comma lambda star, is the minimizer over x is x star equal 3. In other words, a profit maximizing generator is going to want to pick generation equal 3. Furthermore, the Lagrangian, the minimum of the Lagrangian, is equal to the dual, and so if we plug in lambda star to the dual, we will get back that that's equal to the Lagrangian at x star lambda star. And the value of lambda that maximizes the dual, namely lambda star, is also corresponds to being the right price to induce a profit maximizing generator to supply x star equal 3. So if we set the price equal to the Lagrange multiplier, a profit maximizer will respond with a production that causes production to equal demand. So that's true for one generator, but it turns out that when we generalize that for multiple generators, it's also going to be true, and it's going to be central to pricing rules for electricity markets. Okay, that covered duality. Now we're going to look at several types of several types of problems. We're going to start with continuous unconstrained problems. We're then going to move on to equality constraints and inequality constraints, and then both continuous and discrete variables. But for here, we're we're just going to consider unconstrained problems minimized over continuous variables. That is to say, we're going to try to minimize over choices of x in Rn the objective f of x. X here is an element of R to the n. F goes from Rn into R. In practice, our objectives are sometimes only piecewise partially differentiable. However, for convenience here in exhibiting a convenient form of the optimality conditions, we're going to make the assumption that the objective is partially differentiable with continuous partial derivatives. We'll need to consider some extensions when the objective is not so well behaved, when it's got kinks or jumps, and we'll extend those ideas we'll extend our analysis to those cases when we need them. So we're going to consider optimality conditions that'll help us to characterize when we've found a minimizer. So let's look at those optimality conditions for an unconstrained problem. I would expect the conditions that I'm about to describe are pretty familiar to most people watching this material. So in particular, if f is partially differentiable with continuous partial derivatives, and if x star is a local minimizer of f, then the gradient of f evaluated at x star is equal to 0. A point that satisfies gradient of f evaluated at x star is equal to 0, such a point is called a critical point. And critical point could be a minimizer, but it could also be a maximizer or even an inflection point. Unfortunately, without additional information, we're not sure. However, if we add some additional information, we can guarantee that a critical point is a minimizer of our problem. So let's suppose that f is convex, partially differentiable with continuous partials, and let x star in Rn. So compared to the previous theorem, we're now going to assume that f is convex. If the gradient of f is equal to 0, then f of x star is the global minimum of f, and x star is a global minimizer of f over Rn. Convexity is a very powerful property. Let's see an example. Let's consider the objective defined in 4.4. F of x is equal to x1 minus 1 all squared plus x2 minus 3 all squared. We illustrated that previously in 4.2 and 4.3. We already know from figure 4.3 that the minimizer, the unconstrained minimizer of this problem is the point 1, 3. Well, let's evaluate the gradient of f. It's equal to 2x1 minus 1 is the first entry in the gradient. 2x2 minus 3 is the second entry in the gradient. If we plug in x star, we can observe that the gradient of f is equal to 0. Furthermore, if we calculate the Hessian, remember that was something that we could use to characterize convexity. The Hessian is a constant matrix. It is exhibited there. It is a diagonal matrix with entries 2, 2. You can think of that as 2 times the identity matrix, and that matrix has two properties. Number one, it is independent of x, and number two, it is twice the identity matrix, and so is therefore a positive definite matrix. So therefore, by theorem 4.3, del squared f, the Hessian of f, is a positive definite matrix throughout R squared, and therefore f is convex. So by problem 4.8, we have that since gradient of f at x star is equal to 0, we have that x star is indeed a global minimizer of f. Now let's add some constraints. First, some equality constraints. So let's first consider equality constraints that are linear. That is to say, the equality constraint function is an affine function. G of x is equal to ax minus b. And in that case, we typically write the problem in the form 4.24. We want to minimize over choices of x, the objective, f of x, subject to ax equal to b. Theorem 4.9 characterizes optimality conditions. Again, let's suppose that f is partially differentiable with continuous partials. Let's suppose A is in R m by n. In other words, it's an m by n matrix. B is an m vector. If x star is a local minimizer of the problem, then we have the following properties. Two of them, in fact. First of all, there exists a vector lambda star in Rm such that the gradient of f at x star plus A transpose lambda star is equal to 0. And second, Ax star is equal to B. The second condition is pretty obvious. If x star is a minimizer, it better be feasible, which is to say Ax star is equal to B. The first line of the optimality conditions, 425, needs some more explanation. If we go back to the unconstrained conditions, the unconstrained condition would be that the gradient of f is equal to 0. But 425 doesn't say that. It says the gradient of f plus an offset term is equal to 0. That offset term is precisely accounting for the need to trade off the desire to minimize the objective against the need to satisfy the constraints. So the point x star that minimizes x over the points that satisfy the equality constraints, it's not an unconstrained minimizer of f. It's going to have a higher value of objective, and if you check back to the examples, you'll see that's the case. We are still trying to minimize the objective, but we're trying to trade off now minimizing the objective against being feasible. And 425, it turns out, characterizes that trade-off. Lambda star, a vector lambda star that satisfies 425, given an x star that also satisfies 426, is called a vector of Lagrange multipliers. And those conditions, 425, 426, are called the first order necessary conditions, or FONC, for problem 424. How about an example? So let's try a problem we've seen one or two times before. F of x is equal to x1 minus 1 all squared plus x2 minus 3 all squared. A is equal to 1 minus 1. B is equal to 0. The equality constraints, ax equal to b, require that x1 is equal to x2. We've already seen on a figure that the local minimizer, and it's unique, is given by x star equal to 2, 2. And the minimum is f star equal to 2. Does that satisfy our first order necessary conditions? Well, it is feasible. A times x star is definitely equal to 0. But in addition, if we go to the first line of the optimality conditions and evaluate the gradient of f evaluated at x star, that's 2 minus 2. It's not equal to 0. But when I add A transpose times minus 2, turns out to be the right value, A transpose times minus 2, I find that that adds up to the 0 vector. So that's consistent with theorem 4.9 for lambda star equal to minus 2. Again, let's think of an economic interpretation. For a problem with objective f from Rn equal to R, equality constraints Ax equal to B, A is a matrix, B is a vector, we can define the Lagrangian. Lambda is the vector of dual variables for the problem. We can think of the gradients of L with respect to x and lambda, and they are respectively gradient with respect to x of L is gradient of f plus A transpose lambda. The gradient with respect to lambda of the Lagrangian is Ax minus B. Notice that these look very similar to our original optimality conditions, and we can indeed interpret the first order necessary conditions using the Lagrangian. First order necessary conditions imply that x star is in fact a critical point of the Lagrangian that also happens to satisfy the constraints Ax equal to B. A minimizer of the equality constraint problem is also an unconstrained minimizer of the Lagrangian over choices of x given lambda star. And in particular, if the Lagrangian is convex as a function of x, then we can find its minimizer as a point satisfying the gradient with respect to x of the Lagrangian is equal to 0. It'll be an unconstrained minimizer of the Lagrangian. If we know lambda star, we can solve the equality constraint problem by just solving the associated unconstrained problem of minimizing the Lagrangian. We've already seen this in an example. And again, the vector of Lagrange multipliers, lambda star adjusts the unconstrained optimality conditions by A transpose lambda, and that's just enough to balance minimization of the objective against satisfying the constraints. And as again in section 4.2.5, if we interpret the Lagrangian as minus the profit plus a constant, then finding the minimizer of the Lagrangian is equivalent to finding the maximizer of operating profit. And yet again, if we set the price equal to lambda star, we will set up compensation for the operating costs incurred by the firm so that the unconstrained minimization of the operating profits is consistent with minimizing the operating costs subject to the equality constraints. In this case, since we might have multiple constraints, we're going to have prices for multiple commodities. Let's see an example. Back now to a single equality constraint. We've got previous equality constraint problem. The Lagrangian is the objective plus lambda times x1 minus x2. Plugging in what we know to be the Lagrange multiplier, lambda star is equal to minus 2. We get this is the Lagrangian as a function of x and the given value lambda star. Minimizing the Lagrangian, since it's strictly convex, is equivalent to finding a solution of the first order necessary conditions. The first order necessary conditions say the gradient with respect to x of the Lagrangian is equal to 0. Calculating the gradient of this function gives me 2x1 minus 1 minus 2, 2x2 minus 3 plus 2, and if I plug in x star equal to 2, 2, I get 0. In other words, I found the global minimizer of the Lagrangian for lambda, for the value of particular value of of the dual variables equal to the Lagrange multipliers. So here's using this example, I've shown the contour sets of the Lagrangian evaluated at the Lagrange multipliers lambda star equal to -2. The contour sets of the Lagrangian decrease towards the point 2, 2, which is the unconstrained minimizer of the Lagrangian, but is also the constrained minimizer of the original problem. On the other hand, if I don't have the price right, if I don't have the dual variables set equal to the Lagrange multiplier value lambda star, the corresponding minimizer of that Lagrangian will not be the minimizer of the original problem. So let's suppose we pick lambda tilde equal to -5. The contour sets of that Lagrangian evaluated at that particular lambda tilde are illustrated in figure 4.8. And as you can see, the minimizer of this problem is given by something like x1 equal to 3.5 and x2 equal to 0.5. So the unconstrained minimizer of that problem differs from x star. And so in the context of our profit interpretation, where we interpreted a choice of lambda as a price, if we have the wrong price, then profit maximization will induce the wrong behavior. And indeed, what would happen in this particular case is we would not satisfy our equality constraints. So if we know the value of the vector of Lagrange multipliers, we can avoid considering, explicitly at least, the equality constraints. How would we characterize them? How would we figure them out? Well, again, let's revisit the dual function. We've got dual function equal to the inf of the Lagrangian, and the dual problem involves maximizing the dual function over the values of lambda. So the dual equal to the inf of the Lagrangian. The effective domain is the set of lambdas where the dual function is greater than -infinity, and we can consider maximizing that dual function. Let's go back to the example. Here's the Lagrangian. The dual is the inf. That's the inf of this guy. This objective is partially differentiable, and it's strictly convex. So the first order necessary conditions are sufficient. Here are the first order necessary conditions for it. I can solve for the values of x1 and x2 I'll solve for their dependence on lambda. So for a given lambda, the unique solution, and I'll write it x superscript lambda in parentheses, meaning that x depends on lambda, is its first entry is 1 minus lambda 2. That's the entry x1. The entry x2 is 3 plus lambda 2. Plugging those values back into the Lagrangian, I get the value of the dual function, and it's equal to minus lambda squared on 2 minus 2 lambda. So that's the dual function. In the dual problem, I want to maximize it. So what I'm going to do is maximize over lambdas in the effective domain. I'll maximize the dual function. This problem is called the dual problem, and as I've mentioned, the original problem is called the primal problem. And what we'll see is under certain conditions, the minimizer of the inner problem corresponding to lambda star, the maximizer of the dual problem, the corresponding minimizer of the inner problem satisfies the equality constraints. Let's make that a little bit more formal. Let's suppose f is convex and partially differentiable. A is a matrix, B is a vector. Let's consider the primal problem. Let's also consider the dual problem where we maximize the dual. If the primal problem has a minimum, then the dual problem also possesses a maximum. And furthermore, the minimum of the primal problem is equal to the maximum of the dual problem. In other words, there's no duality gap. So this can facilitate finding a solution of the dual problem and finding a solution of the original primal problem. So let's continue with our previous problem. We figured out the dual function. It's partially differentiable with continuous partial derivatives on the whole of R. Since it's concave, the first order necessary conditions to maximize the dual function are sufficient. So if we partially differentiate d, we find that the gradient of d is minus lambda minus 2. That's equal to 0 for lambda star equal to minus 2. And at that value, plugging in lambda star equal minus 2, we get the dual function is equal to 2, which is indeed equal to the minimum of the original problem. And plugging that lambda star into the Lagrangian and minimizing over x, we get a value out which in fact minimizes the original primal problem. So we've been able to solve the original problem by solving a dual problem where the equality constraints have been removed. This type of dualization is particularly helpful when our objective has a particular form. And that form is when the objective is additively separable. So f of x is the sum of terms, each of which depends only on one of the entries of x. So I'll write that as sum from k equal 1 to n of fk of xk, where fk is a function just of the entry xk. Let's consider the dual. So first of all, we calculate the dual function. It's the inf of the Lagrangian. Let's assume that the minimum exists. I can write down the definition of the Lagrangian explicitly, and I can, because of the separability of f, express f as the sum of terms. Furthermore, I'm going to express this term lambda transpose ax as the sum of terms. I'm going to do that by writing ak for the kth column of A. Now, I'll warn you that at various times in this class, sometimes when I put a subscript on a matrix, I'm referring to a column, sometimes I'm referring to a row. But here we're going to be referring to the kth column of A. And in particular, we can think of A times x as the sum across the entries of x of the AK, the kth column, times the kth entry of x. And by rearranging things a little bit, I can think of that as the minimum of the sum of terms now that depend only on particular xk's minus something that doesn't depend on x. And furthermore, the minimum of the sum is equal to the sum of the minimum. What we've just done is taken the inf of the Lagrangian and broken it up into the sum of terms. Each term involves a minimization subproblem, we can call it. So for each fixed lambda, the dual function is the sum of a constant term in lambda and a bunch of one-dimensional optimization subproblems, in particular n subproblems, and they can each be solved independently. We say that we've decomposed the problem by exploiting the separability. And, by the way, each of those decomposed problems corresponds to maximizing the operating profit for the individual firms. And what we'll see is that by choosing a value of price equal to the Lagrange multiplier, we find that that price sets the compensation for operating costs in just such a way that the operating costs incurred by each firm is balanced by the revenue in the right way to make maximizing profit consistent with minimizing the overall cost subject to the equality constraints. And typically in our context, the equality constraints will be supply-demand balance constraints. Let's see an example. In general, this will apply no matter how many entries X has, but in our previous example it had 2 entries and its objective was separable. We can separate the minimum of the Lagrangian into the sum of the minimization of, over x1 plus the minimization over x2. Each of these 2 problems is convex. They can be solved separately for a given lambda, and the result will end up being the same as obtained previously, with the same value of Lagrange multiplier when I maximize the dual over values of lambda. So if the subproblems correspond to operating profit, then the price, pi equal to lambda star, makes the compensation right, so that unconstrained minimization of the operating profits, they don't care about the equality constraints, makes their actions consistent with minimizing overall operating costs subject to the equality constraints. Last issue I want to touch on inequality constraint problems is sensitivity analysis. So let's consider the original problem 424, which was minimizing over x in Rn, f of x subject to ax equal to b. But I'm going to perturb this problem using what I'll call a perturbation vector gamma. Gamma is in Rm, and what I'm going to do is change my equality constraints from ax equal to b to ax equal to b minus gamma. Let's suppose f this time is twice partially differentiable. Let x star and lambda star have the following properties. First of all, they satisfy the first order necessary conditions. Second of all, they satisfy this following condition. This condition says that for any delta x that's not equal to 0 and such that a times delta x is equal to 0, when I multiply del squared f on the left by delta x transpose and on the right by delta x, that gives me a number that's greater than 0. This type of expression should look familiar to the definition of positive definiteness of a matrix, and indeed this condition is described as saying that the Hessian is positive definite, but not positive definite for on all delta x. It's positive definite for those delta x's in the so-called null space of A. So this is a technical condition. Basically, it comes down to requiring that x star and lambda star satisfy the first order necessary conditions and a little bit more. Well, if these conditions are satisfied, then for values of gamma in a neighborhood of gamma equal to 0, in other words, for some open set containing gamma equals 0, we'll find that if we plug a value of gamma in that open set into problem 435 and solve problem 435 for that perturbation value, there will be a local minimum of the perturbed problem. There'll be a local minimizer and Lagrange multipliers. Moreover, all of those things thought of as a function of gamma will be partially differentiable with respect to gamma. They'll have continuous partial derivatives. And finally, the sensitivity of the local minimum to gamma evaluated at gamma equals 0 is equal to lambda star transpose. If f is convex, then the minimizers and minima are not just local, but they're also global. The conditions for the sensitivity theorem to hold are not always satisfied by the problems we study, but nevertheless, sensitivity analysis can give us very powerful insights. Part of the difficulty in proving it is to prove that indeed the minimum exists and that the minimizer exists and is partially differentiable. But if we assume that they are, in other words, we assume that for various values of gamma, the minimum and minimizer of the problem are well defined and that they are partially differentiable, then we can see why the sensitivity is given by the Lagrange multipliers. The reason is as follows. If we've got our problem 435 and a perturbation vector, then if we consider the change delta x star in the minimizer of the perturbed problem compared to the original problem, if we wanted to estimate the difference between the minimizer of the original problem, the difference between the minimum of the original problem. The minimum of the original problem is f of x star, where x star is the minimizer of the original problem. If we want to know how much that differs from the minimum of the perturbed problem, where the minimum of the perturbed problem is x star plus delta x star for some unknown delta x star, we could estimate that difference in terms of the gradient of f transpose times delta x star. And as delta x star gets smaller and it goes to 0, we'd expect the left and right hand sides of this expression to get closer and closer to being equal. Well, the first order necessary conditions tells us that the gradient of f at x star, in other words, at the base case problem where gamma is equal to 0, that plus A transpose lambda star adds up to 0. So I can substitute gradient of f transpose delta x by minus lambda star transpose A delta x. However, A delta x has to be equal to minus gamma. Why is that? Because if x star plus delta x star is feasible for the perturbed problem, we have that A times x star plus delta x star is equal to B minus gamma. Crossing off, cancelling off B and AX star, we find that A delta X star is equal to minus gamma. So that gives us the last line. What have we just shown? The difference between the minimum of the perturbed problem and the minimum of the original problem is proportional to gamma. And the proportionality is approximately proportional to gamma, and that proportionality is given by lambda star transpose. And this is true for every gamma. As gamma goes to 0, this would enable us to evaluate the derivative of the change in the minimum with respect to gamma, and it would tell us that that derivative or sensitivity is lambda star transpose. So we can interpret the Lagrange multipliers as the sensitivity of the minimum to changes in gamma. In many problems, we can think of the specification of the constraints as representing some judgment about the availability of resources. Well, if we know the cost of those resources and compare them to the Lagrange multipliers, that can help us to trade off the change in the optimal objective against the cost of, say, purchasing some additional resources. So in particular, if the equality constraint is supply-demand balance, then the Lagrange multiplier provides us information about the marginal cost of meeting additional demand. Let's see an example of that before we finish this section. We'll use the same problem we've looked at before. We found that the Lagrange multipliers for this problem was lambda star is equal to minus 2. Let's suppose that the equality constraints changed from AX equal B to AX equals B minus gamma. If gamma is small enough, then the minimum of the perturbed problem differs from the minimum of the original problem by approximately lambda star transpose times gamma, or minus 2 times gamma. We can use that to evaluate the change in the minimum when we perturb the problem. That completes our discussion of equality constrained problems.